Has anybody tried to log into WPI yet today? It's not sending me a text message. We're sorry, we're having trouble. Let's try again. Oh, this time it worked. 275 119. Verify. Look at that. I'm in. Okay. We did say we were going to do it in person, right? So everybody that's not here just overslept, you think? Maybe. I just emailed the class with the link to the live videos, so hopefully we'll get everybody here. And let me just take a look. All right. Oh, there's a couple people watching. Okay. If you are watching live video, could you please give me a comment to tell me that the audio works fine? Somebody? Anybody? Maybe? Okay. All right, well, I'm going to go with it. All right, so this week we said we were going to talk about 3 to 5 axis machining, right? And that's the topic, sort of the theme of everybody's group project for the term also. So I think it's a good place for us to start. First off, for all the groups 1, 2, 3, 4, and 5. Remind me again, group 1, what's your what's the thing that you're going to have to focus on in order to get your project done? Is anybody here from group 1? You guys, right? So what is it?
The thing that we're making?
I mean, you're making the can crusher thing. I remember that. But what was the 3 to 5 axis machining topic that was going to be most important to you guys? I think I know. I'm checking to see if you guys know.
I'm not sure.
So last week when we talked about it on Thursday, I think we said you're definitely going to have to do some. It's really a lot of 2+1 axis machining for a lot of the components for your part. I think we even said that some of the components you might be able to wire cut, right? But so you're looking at mostly 2+1 axis. And group 2, where's group 2? You guys are over here. Okay. So remind me again which one of your project is. For some reason, I remember group 1 was the can crusher.
The
Chessboard. Okay. So you're going to do mill turn, right?
Yeah.
And group 3? Yep.
Probably also mill turn.
So you're going to do some mill turn. What are you making again?
Making the axle axles, wheels.
Right. So it's more milling and turning, but not mill turn in the same setup.
Yeah.
So and then maybe some wire stuff to make the gears, right? Group 4. Yeah.
Fourth axis.
So you need to do fourth axis milling. In group 5, the puzzle. Have you guys figured that out yet? Is the group 5 here? Oh, back in the back. So 2 plus 1, because most of your parts are going to be prismatic, right?
Yeah.
Right, because you're thinking you're going to make some prismatic parts that fit together to make up that 3D puzzle. Okay, so all right, so we've said we're going to have to do 2 plus 1. Well, this is really milling, right? We're going to do some 4-axis milling. We're going to do some mill turns. So you're going to do some turning operations and milling operations on the same part in the same setup. And you're going to do some milling and turning separately. And so the turning you're going to need to do, you're turning the wheels mostly, right? Right? You guys are over here. Okay. You're turning the wheels, and then you're going to mill out the other parts. So we're going to do these operations, and the class is about computer-aided manufacturing. So what are the steps? So if for all of these things, they've got steps in common. What are the steps in common that you're going to have to do? Yep.
Develop like a digital model for your parts.
So you need a digital model for your model of parts. So the first thing you're going to need is you need to know what it is you're going to make. And so beyond the model, are you going to need anything else to define what it is you're going to make? So could you do it with just a model? Is it possible to have a solid model of a part and make a machined part? Yep.
You also need like tool paths.
Well, so we're going to have to take that model and turn it into those tool paths, right? But first thing we're going to need is we're going to need a model. We might need drawings. Often the drawings are especially important if you're going to be giving the job to somebody else to make the parts. So if you're the designer and you're going to hire out the manufacturing from somewhere else, then just giving somebody the model doesn't necessarily give them enough information to make your parts. But if you give them the model plus drawings, then you've got a chance. Oh, some people are talking online here. So we're going to need some sort of a computer setup and some sort of starting dimensions for our stock material, right? So once we've got our model, our drawings, once we've defined the design, we've got to know what stock material we're going to cut it out of. This marker sucks. Let's try this one. And so the designer creates all this stuff. The designer creates the model, the parts, the drawings. The designer decides what the stock material will be, so what type of material it will be. But when we get to manufacturing, we've got to decide what particular piece of stock material we're going to use. And so let's take the example of the chessboard, or the chess. It's not the chessboard; it's the chess pieces, right? Chessboard would be kind of boring to make. The chess pieces are pretty cool, though. So what's the typical stock material we're going to use for a chess piece going to look like?
I'd say most pieces are made out of wood.
Okay, you guys aren't going to use wood, though, right? So what would the shape of the stock material probably be for your part? Yep.
We were thinking like 1-inch round stock.
So we're going to start with 1-inch round stock. So this diameter is 1 inch, right? And what's this diameter? Yeah. So as the manufacturing engineer, you got to decide how. So you pick 1 inch round. You pick the 1 inch diameter in order to, because your part fits inside 1 inch diameter, right? That's really how you decide that global spec or that overall size of your material. Your part fits inside 1 inch diameter. But how long should the piece be? Doesn't have to be from that group. You imagine making a chess piece, right? How long does the piece need to be? So it needs to be at least as long as the workpiece, right? Or as the part. It's got to be as long as the part, but then you have to hold it. So if the part is out here, so we're making a pawn. Right, that sort of looks like a pawn, I guess. And it's sort of in the center of the material. So we need this much material to make the part. But we also need to hold the part somehow in the machine tool. So we need at least this much material to hold on to. Does that make sense? So we've got to have at least that much material. Now, what if we're going to make a lot of parts all at once? So what if you're going to make the entire chess set? So how tall is each chess piece? On average, say 3 inches. So if the chess piece is average 3 inches tall, and how many chess pieces are we going to make? It's 32 chess pieces. So what do we need? 3 times 32 is what? 96 inches. So we're going to need at least 96 inches of material. Do we need to add? So let's say that this is 1 inch here. The area that we're going to clamp on in the chuck jaws for the lathe is typically about 1 inch. Do we need to add 1 inch to each one of these 3 inches? Not if we're going to make one piece after the other, right? We need 96 inches plus 3 inches at least. Because that last piece, we still got to hold on to 3 inches. Is that enough information to order the stock material for your chessboard, chess pieces? So if I've got, 96 inches, that's what, 8 feet? Something like that, something like 8 feet. If I've got 8 feet of stock material in my lathe spinning around, what's going to happen? So if here's the chuck of the lathe, we've got 8 feet of material back in the lathe. The whole thing. So what kind of speeds do you think you're going to spin your part to make your pawn? I'll tell you that the lathe you're going to use spins to 6,000 RPM. So if I've got 8 feet by 1 inch diameter, let's say you top out at 4,500 RPM, how much energy is in that workpiece when it's spinning? A lot. So what's going to happen out here as you spin it around? It's going to vibrate. If you're not supporting it out here very stably, it's going to want to do this, right? You got a ginormous lever arm out here. So if you, where's the center of mass? The center of mass is somewhere around here compared to the lever arm, right? So if you get a little bit uncentered, you're going to have a giant force this way, and then this way, and then this way, and the material's going to fail. It's going to bend. Maybe, if you're lucky, it's going to fail before it whips around and kills somebody that's standing over here, right? So we're not going to have 96 inches plus 3 inches. We're going to have to cut it a couple times. Now the spindles in the lathe. Yep.
Well, I guess in like our particular case, doesn't the mill turn have a bar feeder?
It does. But the maximum bar length is going to be what you can contain inside the spindle liner, which in this case is around 3 feet.
Okay.
You call it 30 inches. So really you're going to have three, if you did 3 32-inch bars plus 3 inches, so maybe 3 36-inch bars, then you could probably get your whole chest set out of it. So that's one of the first things you're going to have to think of. So you're going to need 8 feet of material. Do you need any more material than that? Yeah. You're probably going to want some material for a setup piece. So let's say I've never made I've never used the mill turn machine, and I've never made a chest set on a lathe before. I'm probably going to screw some of the parts up, right? So the first thing I would do would probably be double that. Like I'm going to say, I need 8 feet of material. Let's get 16 feet of material just to make sure that we probably won't use all that. But let's get some extra material. And so you're in luck, chest group, because we have a bunch of 1-inch round aluminum that you can use for this project. So you don't have to worry about acquiring the material. All right, so that's the round stock. So we've got to get stock material. Now, what if we're doing a milled part and maybe the black will work now. Oh, I know. They dry out, right? Well, this thing is definitely dried out. That's going to totally work better now. No, not really. Yeah, not at all. I do know that you can use that as fuel to run your ME1800 Stirling engine, though. We've done that before. All right, last try. Aiden, can you do me a favor? Go somewhere and find some whiteboard markers that have whiteboard marker in them. Oh, you're my favorite. Which group are you in?
Puzzle group.
Give the puzzle group extra points for this week. Don't forget to take those back later. All right, so I'm not saying yours works any better than the one I had, though. Take some of those points back. There we go. Blue works. All right. It's actually, they did studies on education. Well, I don't know. They did a study about whiteboard markers. They totally said that the students, the audience, retains more information if you use blue on a white background. I think the study was funded by the council to sell blue whiteboard markers, but I'm not certain. All right, so puzzle group. How big are your pieces going to be?
Relatively small, like a couple inches.
So
But there's
draw me an example of what one of your parts is going to look like. Now, you don't have to have decided yet, but just give me an idea. See how I did that? I delegated. It's also a management class.
the one piece we got. My art skills are not coming.
Why the heck do you think I wanted you to draw the art instead of me?
Something along the lines.
Yeah, there you go.
So something like that, but that's going to be like.
All right, that's good. That gives us an idea, right? Guys, yeah, at home you should be able to see that too. All right, so we're going to make a part that's, so I'm going to draw the the front view of this part now. So you gave us a nice little isometric projection there. So we get the front view of this part. Something like that. And then a side view. Something like that. Did I get my drawing skills correct? Perfect. All right, so give me some dimensions. What's this dimension? And so what's that dimension? And they don't have to be accurate. I'm just trying to get an example for the class, right? An inch, 1. And so we will say down here, not to scale. In case our manufacturing partners decide to measure off the drawing. Not to scale. Okay. So half an inch, since like it looks square, but it's not. Okay. How about, we're not supposed to dimension to a hidden line, right? Is that one of the rules? Never dimension to a hidden line? Yeah, I'm a rule breaker. What's this? A half inch again? Okay. And then, so we'll do 0.5 here for this, for the example. And what's the overall length then? We'll call it 3. I think 3 makes it look more like the way I drew it. Okay. So if this is what our part looks like, what's the stock material need to look like? Because we got our models. We got our models for our turning parts. We've got our models now for one of the parts for our puzzle. Yep. That's the purpose of the discussion, to answer that question. What's our stock material need to look like? So the question was, do you need extra material to hold on to? And so how are we going to make this part? Somebody walk me through the steps for machining this part. It does not have to be somebody from the puzzle group. It might be better if it's not somebody from the puzzle group. Because the first thing we had to do, once we've picked our thing and we've got some stock material, is we've got to say what processes are we going to do and in what order, right? So next past stock material is decide. So we haven't even gotten to the computer-aided part yet, have we? This is all the human computer. We haven't even gotten to the computer-aided part. So decide how to make. So once we've got it, so how are we going to make it?
So I think you could maybe fixture it in the mill such that you can probe all the sides, and then you can machine basically like half of it out, the top half, and then you would flip it in the mill and then machine out the
All right.
half.
So what you're saying is you want to hold it so that the stock material's got this side up here, and you want to machine this material away?
I was going to say, so like rotate it 90 degrees.
Rotate it 90 degrees. So take this view and rotate it down 90 degrees.
Yes.
Okay. All of these things are possible. Right. So the first thing we got to do, so if our part is a 1 inch by ½ inch wide kind of thing, our stock material has got to be at least 1 inch tall by ½ inch wide, right? So we're going to buy a bar of stock material. If all of the parts fit in this envelope, maybe you need bigger piece for some of your parts. But if all the parts fit in this envelope, then we'll probably get a bar of material that's 1 inch by ½ inch by some length, right? Does that make sense? We could also get a ½ inch thick plate of material. So we could also get a plate of material that's a ½ inch thick. which is the better choice? Yeah.
With the bar, like the rectangular bar, could you still like feed it through like a rod?
Actually, you could. You could mill turn these parts, but typically you wouldn't. Yeah, you can take rectangular stock or square stock or hexagonal stock, and you can put it in a lathe and you can hold it. I think it doesn't violate laws of physics to do that. I've never actually seen somebody do it with like not square rectangular stock and bar feed it. But there would be a way to automate that process. I think I typically would feed it through in a milling machine instead of in a lathe. And I could envision in my head how to automate the process. So yeah, certainly you could do it. So we could get a plate like this or a bar like this. Which one should we choose for our process? Yep. So if we got the bar, I don't know. Well, we can pick, right? Typically they come in like 12 foot, 6 foot, 3 foot. Yep.
I think it would depend. If you were just doing that part, I would say do it on a bar. But if you were doing multiple parts on the same stock material, I would say the plate would probably be best if it fit.
Okay, so we could nest parts inside. So let's say you had like 15 of these parts that all then fit together to make your puzzle. And maybe they're all the same exact shape, or maybe there's some different shapes, right? So you could I guess I'm not very good at art either. Right? You could nest the parts in like this. And you could fill up a sheet with those kind of parts like that. Okay. If you do this, what process are you going to use to cut the parts? How do you envision cutting the parts? Yep.
You could wire EDM that.
So I could take my wire EDM and I could cut around the parts like this. I may have to make some holes to get the wire through for each of those parts. So I could do that, and I could drop the parts out, or I could have the wire come in from the side. Yep.
Could you have the mill carve it out from above and then somehow separate it above?
So could you mill them from the top with an end mill? So if we did that, we could come in with our end mill. Might have to space this one out a little bit. But you could have a tool path that went zigzagging through like that. When you did that, your part, and so you were thinking not go all the way through so it's still held on to something?
Right.
Yeah. So you could do that. Don't go all the way through so that you're still held on to something. So you could put like 4 bolts to hold the plate down in the milling machine. And then you could have your mill trace around all those parts, or basically make a giant pocket and leave these pieces as islands. But if you do that, each piece so these corners could be square corners. And these corners will have, at a minimum, the radius of the end mill, right? So yes, you can. I mean, likewise here with the wire EDM, in that corner, it's going to be the radius of the wire. Right? The wires are really small. You're going to have a hard time seeing that radius, but it's going to be there. What else could we do to make the parts this way? Because if you did this, you're going to have a secondary operation, right? I'm guessing your puzzle pieces wanted to have right angles here,
Well,
sharp corners.
we were discussing that the sharp corners, like for fitting the puzzle together, may be a little tough to.
Okay, so maybe you want to have all roundy corners, and maybe this method works for you. Maybe it doesn't. If you need to have sharp corners here, you could totally do that. And so then let's say we went and we left a little bit of material so that all those parts are then basically like a bunch of Legos that are stuck down to one of those flat Lego plates when you're finished, right? So then a couple of different things you could do. You could take like a bandsaw or something and you could separate those pieces individually from each other. Then hold them by clamping on this piece with the Lego plate thing left on top. Flip it over and you could face it off and remove that material. That'd be one thing you could do. You could make a fixture that holds all of them at once and just face off that material, right? Or you could cut all the way through when they're in the plate. What happens if you cut all the way through when they're in the plate? From the top to the bottom. Yeah.
You need like some sort of like sacrificial like material.
So you may want to have some sacrificial material underneath it so that you don't cut into the milling machine table. Thank you very much. Don't cut into the milling machine table on accident. Yeah, don't do it on purpose either. Although if you own the milling machine table, I suppose that's up to you. It's one of our rules in the lab, don't cut the fixture on accident. It might be okay to do it on purpose, but don't do it on accident. Right, so you would put something underneath it when you cut through. What else is going to happen, though? What happens at the instant? So let's say your tool path to cut it goes around. What happens when the tool gets here? Yeah. The part breaks loose, and then what happens? So at the instant when the part breaks loose, so let's say it breaks loose when your tool's right about here, you've got a cutting edge on your tool. We're spinning clockwise. All right, so we got a cutting edge on the tool that's pushing the workpiece this way, right? So the force from the tool on the workpiece is up because of the spiral on the flutes. So it's trying to pull it out of the fixture coming up, but it's also pushing it in this direction. So what's going to happen when it is no longer constrained? Yep.
Well, I know it's not going to stay where it was.
It's certainly not going to stay where it was because it's got hundreds, maybe 1,000 pounds of force pushing it sideways. And it's not very heavy, right? Because you can make these out of aluminum. So it's not very heavy. It's going to get flung this way. Now, but it's inside right, you just cut around it. So there's material out here around it, right? So it's going to become disassociated with the stock material, disattached, right? It's going to fly over. It's going to bounce off this side and come back and hit the tool. That's what's going to happen. And the edge of the flute on the tool is going to break. Which is why we don't like to cut them off and drop them out. Now, is it possible to do it without breaking the tool? Yes. Is it possible? Is it very likely to break the tool when you break them out like that? Yes. That's why we don't like to do that unless we've done something to hold this part in place when it cuts off. Right? So if this part had two holes in it, and you were fixturing the plate down by screwing down through these holes, and you were also holding the outside of the plate down, then you could cut through and cut parts out all day long, and these aren't going to go anywhere because you're holding them in place. Right, so that's one of the things that you can do. But so you've got to come up with a plan for how you're going to turn your stock material into the workpiece, right, into the thing that you want. And so the other thing you could do if you wanted to cut these shapes out of a plate, water jet, laser. Those are all, we don't have water jet or laser here that could do that, but those are processes that could cut that, yeah.
Could we have a flat plate and mill almost out of like the plate
And then cast some material in it.
cast it.
Yeah. So that would be another way. So certainly if you were going to mass production of this thing, you might want to mold them or cast them, something like that, right? I think if you buy, I'm channeling Christmas Day after dinner, playing games in the living room, because my aunt and uncle's house, where we always go for Christmas, except for this year and last year, they have all these kind of puzzles and stuff in the living room. And I think a lot of the metal ones are cast. So the pieces, some of them are bent wire, but a lot of them are cast also. So yeah, you could do that. We're not going to do that in this class. But yeah, there's all. I think I would do investment casting though. I think I would machine the positive out of like plastic or wax or something like that. Put it inside sand or something that'll pack tightly around it, and then pour the hot metal to remove that. I don't think I would. I don't know. You could injection mold them too. So, all right. So there's some different processes that you can do that. So this week for your projects, right? This week for your projects, you should have decided what the part's going to look like and what the stock material is going to look like. And in order to do what's the part going to look like, what's the stock material going to look like, you need to have figured out in your mind at least what the processes are to make this. I think if I was making these parts, I would make them out of bar stock like this, and I would probably get my bar stock oversized. Maybe I would get 625 by 1 1/8 if I could get it, or 1 1/4 if I can't get it, so that I have some material to hold on to while I make it, so that I can machine all of the faces and have a machine surface on the outside of the part. Whereas if we got just 1/2 inch wide bar stock by 1 inch tall, you wouldn't be able to touch the sides or the top and bottom with the tool. It would make it faster to make the parts, but it would be a different surface. It would be the as extruded or as rolled surface on the material, as opposed to a machine surface. So those are the things that you want to consider. Yeah, I think if they were square inside corners like this, I think I would get 1 1/4 tall by 625 or 0.75 wide if I couldn't get 625 wide. I would hold it in the vise on the bottom 1/4 inch or so. And I would make this entire shape from the top, then flip it over, hold it by that, and face off the bottom. So I would do it in 2 setups. But you're going to want to have figured out what all the parts look like, or what this could, right? If you're going to refine your design later, it could change. But know approximately what all the parts are going to look like and what processes you're going to use to make the parts, so that you can specify your stock material. So that by Thursday, we're going to know exactly what stock material everybody needs and can make sure that we have that. Now, the next step after figure out models and stock material in our CNC machining. Yep.
Are we given a budget for the stock material?
That's why I want to know by Thursday, so we can figure that out. So like the chess piece guys, I know I have their material on hand. Your stuff depends on what you decide to go with and what process you want to go with. And so for the Thursday presentation, have that figured out. Decide what's the stock material going to look like. Also, yeah.
There's going to be some bigger components than others.
Yeah, you can figure out independently stock material for each component and process for each component. These were just examples for what we're going to do, right? So for the wagon trolley thing there, the train trolley, they may make the carriage, I don't know, they might make it out of wood, right? Traditionally, those would be made out of wood with metal fasteners around it. So they may decide to use different types of materials too. And chest group, we may want to do 2 materials. So if that's what you want to do, figure that out. What I would ask you to do on the stock material is don't order it, don't buy it, but go to McMaster-Carr. Go to McMasterCarr.com and find out pricing for material that you could use so as if you were going to buy it and as if you were proposing to buy it from me before we order anything. And it might be that we have to order it, but before we order anything, we're going to go through the shop and make sure we don't have that laying around or something similar. But for Thursday, have models of your parts and have your stock material picked out and use McMaster-Carr as a reference. And so give us a proposed budget for how much it'll cost to buy the material. Justify how much material you need to do your project, including extra material for setup parts, things like that. Okay? So once we've done that, though, what's the next thing we have to do in order to make our CNC parts? So if we've got our models and we know that we have stock material, that's really the first 2 things you have to have. If you don't have models, you can't get stock material because you don't know how big it needs to be, right? If you don't have stock material, you actually don't know how to make to do the next step, right? What's the next step after you've got your stock material and you've decided in your head what the processes are going to be? It doesn't have to be a spree, but I would at my next step go to some tool to create tool paths, right? And so somebody doing their presentation last week mentioned Fusion, right? Which group was that? I can't remember. You guys can use Fusion if you want to. You will have less support from the lab staff than if you use a spree, but you totally can use Fusion to do this stuff also. Although there's a lot of, oh, hey, I got my little neck warmer thing on. My neck warmer fake mask thing. I'll take this off. Oh, no, I totally. Does that make me look gangsta? Different. Okay. I bet you there was a lot of audio when I took that off. So Ryan asked, is there a set budget for the projects? No, there's no set budget. We're going to just figure that out as we go. Okay. So what's next? Whether we're doing turning or milling in the CAM software, we have to, in our mind, have decided what the operation is going to look like before we start doing it. Does that make sense to everybody? I mean, you could next week or the week after, whenever we start talking about automating using the CAM software, I think it still helps if you, the engineer, has decided in your mind what the toolpath's going to look like. Can the software figure it out for you? Yes. But the purpose of our talking about it is really about how to tell the software to figure it out for you, not to have the software just do it for you, right? Because we could easily make all these. What's the easiest way to make all these parts? So say you were a design engineer at a small startup company, and you were making this part as a product. What would be the easiest way to get your prototypes made? I heard a vote for 3D printing. What else? I got 3D printing on the online too. 2 votes for 3D printing. What else? What else would be the easiest way? Somebody says 3D printing. Does anybody disagree with 3D printing?
Injection molding in the chat.
All right, somebody says injection molding.
And also laser cut in the chat.
Injection. Yep. I still haven't seen what I think is the easiest way.
This, like,
So if you're the design engineer, you're at a company, you've got this new product you're going to come out with, and it is the thing that you've decided to make for your project here. What's the easiest way to get the first prototype? Yeah.
Cardboard.
All right, so cardboard. Anything else coming through? So, all right, so I got laser cut, casting, water jet. Somebody else, can you read the other comments there?
Hire it out.
What else?
Send overseas. Same thing.
Yeah, I said outsource. Right, could be. It doesn't have to be overseas for it to be outsourced. It could be across the parking lot, right? So what's the easiest way? That's the easiest way, right? Fastest thing to do is make somebody else deal with the manufacturing part of it. So this is probably the easiest way. As to like laser cut, water jet, casting, 3D print, injection mold, cardboard, as to all those other things, it's going to depend on the part, right? It's going to depend on your internal capacity. What can you do in-house? So if you don't want to outsource, what can you do in-house to make the part? And so as the engineer, you're going to have to think about these things. Now, what goes into injection molding? I don't think I would put that up at the top, but go ahead. Yeah. I guess I did put it at the top. I put it at the top and the center when I wrote it
I
down.
would agree, because I think it is like one of the more difficult ways to like manufacture anything.
Are you kidding?
Well,
They make stuff, it's like 37 seconds to make a plastic milk crate.
But you have to like make the mold
It-
first.
Oh, you have to invest in the tooling. Yes, the problem with that 37-second process is you might have $100,000 in the tooling. Not counting the machine that the tooling goes in, just the stuff that goes in there, maybe 50,000, depends on how complex the part is. Casting, you would think would be similar, right? But it is totally possible to quickly and cheaply 3D print an investment, put it in the thing, and pour the metal. So casting, and why not just 3D print it? Then if you're going to 3D print it and then use that as the investment to do investment casting. Yeah.
Well, it all like a lot of this depends on like what
Depends
you
on what the
need for
material
everything.
needs to be, right? So you're going to do this process. Now you might outsource to have them do this process, right? But there's companies out there that will do short production run casting. There's companies out there that will do short production run injection molding for you if you're outsourcing that, if you don't have that. You said cardboard, right? What do you like about cardboard? It's really cheap, right? You can get a quick idea. You can glue stuff. I mean, you could paper mache, right? You could get some quick ideas. So it also depends on what fidelity do you need for that prototype also, right? What's the purpose? When we were rearranging the equipment in the machine shop, one of the first things we did was we made a model of the room. And then we made models of all the machines and we digitally put them together, right? So even before getting the prototype, you might digitally look at your things. Do they fit together as you've envisioned making them? So you can do all that. Then we printed on cardboard the layout of the shop, and we 3D printed the models of all the machines and like the little barrels that the chips go in and stuff, and we placed them all around to decide, is it going to fit? That almost worked, but it was a good tool to use. All right, so once we've decided that we're not going to outsource, although you can get super complex CNC machined parts in about 3 weeks turnaround from outsourcing them. If you want it faster than 3 weeks, you probably need to be able to make it in-house. All right, so let's assume that we've decided we're going to do CNC machining. And we're going to do it in-house, and we've got our model, we've got our stock material, and we've got in our mind how we're going to do this. We use the CAM software now to help create tool paths. So I want to spend the next few minutes Okay. All right, I want to spend the next few minutes. Hey, Hayden, shout out if somebody has a good comment. Talking about what does the tool path include? All tool paths include certain things. So what are the things that all tool paths include? Doesn't matter if it's CNC machining, milling, turning. I'm going to even include wire EDM. All tool paths include these things.
Like there's usually like a section of code that finds an origin.
All right, so we need to have an origin or X, Y, Z. You do not have to program in Cartesian coordinates, but I'm going to program in Cartesian coordinates when I talk to you guys, because that's the one that's easiest for me to think about. But it's possible to use any coordinate system that you could transfer this into. But X, Y, Z, we usually call it the zero. It's so you said that one, right? So explain to us what the origin is, what the XYZ zero is.
So like if you have like that puzzle piece, for example, you want like a datum point, like one point on that part that all of your features are measured from. So you have like one common place to do all of that measuring from.
So we've got our puzzle piece. Let's say we've got our stock material that the puzzle piece is going to fit inside.
0 plus we support her.
So if the green represents the stock material that the puzzle piece fits inside, the puzzle piece fits inside the stock material here. Where should our 0 point be? So we need a 0 point. We need an origin. Yeah, go ahead. So we could put it on this corner. All right, so that's, if I go to the front, is that over here then? Now, I meant for that to be a question, but instead I drew it where it should be. Do you notice the 0 point is on the workpiece material and not on the puzzle piece? Could we put the 0 on the puzzle piece? Right, so we could alternately put the 0 here. Yep.
Don't you usually want to start off the part?
It's really a matter of style and what you're thinking about, right? So as the designer, we tend to think about the workpiece. Is that true? As the designer, or the finished part, right? We tend to think about the thing we want as the designer. As the manufacturer, sometimes we think about the thing we want. We certainly have to think about the thing we want when it comes to the inspection step, right? But when we're thinking about setting up the machine, it's much easier for us to think about the stock material because that's what we have in our hand when we're setting up the machine. Does that make sense? So it's kind of a style thing about whether you put the 0 on the stock material or on the finished part. When you program it, you do have to tell the setup person which one you picked. Right? That's an important piece of information to convey. Now, why is it that we even have a 0 relative to the part here? Right, because the machine itself, if I've got the machine tool here, I've got my spindle. I got my spindle with my tool in it. I got my table underneath it. I can put my part here on the table. So there is an XYZ 0 here, right? That's the machine 0. So why do I even need this one? Why don't I just write my program relative to here? Because I could reference this 0 and tell the tool, all right, go over here 15 inches. Go over here 6 inches, right? I could do that. So not all pieces of stock material are going to be the same. Did you have your hand up or were we stretching? Not all pieces of stock material will be the same. We might not always put it in exactly the same place in the machine tool. And we may not always use the same machine tool. Right? So that's why we want to have this origin that references from the stock material or the work or the finished part, depending on which one we prefer, rather than the XYZ 0 of the machine. Now, when we've done that, when we get to setting up the machine, what do we have to do after we put the stock material in the machine? As we're doing setup, because we're doing the programming and the setup and making the parts in the class, right? So if we've specified as the programmer, as the manufacturing engineer, we've specified where we want our origin to be. When we get to set up the machine, what's the first thing we're going to do? We'll typically use the probes in the machines, but we're going to tell the machine tool where the 0 is that it's going to do. And so you'll do that, and what it does is it measures basically this distance and this distance by physically moving the machine, and it knows where it is in its coordinate system whenever it's moving, right? Physically move the machine until the spindle is above the XY 0 and say, hey, this is where the XY 0 is, right? So when we use the probe, it comes in and it touches the side maybe, and it says, all right, so here's where the Y0 is, and it touches this side and it says that's where the X0 is, and it knows the intersection of those two planes, is where the XY zero is. And then the Z zero is, so here I put it on the top of the stock material because the top of the stock material is pretty visible inside the machine tool, right? When I go to set it up, I usually know where the top of the stock material is. And so we'll often come in, change tools here, and we'll have our probe in there. And the probe will come down, and so maybe it touches the side, it gets the X, gets the Y. Then we come down on the top, and we touch the top with our probe. What's it actually measuring? Right, so the top of the bottom of the probe touches the top of the workpiece, and it says, all right, here I am, here's where the top of the part is. What has it actually measured, if you think through what it knows? Yep.
Well, so the machine, if I remember from 1800, like knows how long the probe is, as well as like a pretty damn accurate measurement of your radius on the ruby of the probe. So there's like also a tiny like plus or minus like whatever the radius on that probe is.
I'm on a ASME standards committee, and I just wonder if I could get the phrase "damn accurate" to become a standardized term. So when you said that, I couldn't think of anything but that. I was like, what if we could write that into the standard somehow and clearly define "damn accurate"? I'm picking on you, but it's to make a broader point. Who's ever had to write a paper, engineering report? Few of us. We've had to write something. Who's ever used the word "very" in a report? Very. Like this was a very good way to do this thing. We had to be very accurate when we set up the machine, things like that, right? Could you replace the word "very" with the word "damn"? Right? So my PC advisor taught me this. He said, if you could replace the word "very" with the word "damn," go ahead and do it. and then do you find and replace all and just delete all of the damns before you hand the paper in. It never adds semantic value to an engineering paper. but yeah, so we do calibrate the length of the probe. So before you use it to probe the part, and that was what you were trying to get to, right?
Yeah.
Yeah. So we calibrate the length of the probe, and we calibrate it by touching the probe tip off of. Yeah, I'm not going to draw this very well, but sure. We've got a tool probe over here that's in the machine also, right? And so what we do is we touch the top of the probe to the top of the tool tip, and we know then the length of the probe relative to the position of the tool tip. So we know that when the probe touches the tool probe, we know where the spindle is. So we know the length here relative to this. And then when we measure here to here, we're really measuring what's the height of our Z relative to that surface that we calibrated from. So it's taking both of those numbers, and then after we tool change, all of the tools that we use to cut this program have to also be measured from the tip of that tool probe. Does that make sense? So that's how we're setting it up. So the Z is going to be relative to some arbitrary position, right? This is just a thing that's bolted down to the table. It could, in fact, just be a spot on the table. And instead of the fancy probe, right, instead of that fancy probe, we could put a dial indicator in here. The dial spins around as it goes up and down, right? And we could use a dial indicator to say, all right, what's the difference between here and here, and then measure all of our tools relative to here. So that fancy probe, when we're doing Z, is roughly the same as a dial indicator. So it just knows when that surface is. We could do it without any tool and just bring the spindle down and touch the end of the spindle to the table, and then touch the end of the spindle to our workpiece. Why don't we do it that way? That would be cheaper. We wouldn't have to buy those couple $1,000 probes, right? That probe, the probe body, the little ruby tip, right? So this is ceramic. That's a little ruby, and you get the probe body, and then it attaches to a tool holder that goes in the spindle. Anybody know how much these cost? We break those all the time. Somebody should know how much they cost. Yep.
Isn't it like $60-ish?
$97. I've seen prices in that range, but they're not exactly the same probe tip. So $97 for one of those. Anybody know how much one of these cost? RBE. Anybody know what RBE stands for? Not robotics engineering. But I suppose it stands for that here at WPI. Repair by exchange. The probe manufacturer that makes the probes for our machines has this great policy. If you can find most of the pieces and you know the serial number, you don't have to be able to read the serial number on the side of the probe anymore, but you have to know what it is. You can send them back most of the pieces, and for $2,000, they will send you a new probe. Costs about $5,000 to buy them new if you don't already have one to send back. So yeah. Why did we bring that up? Oh, and how do I know how much the RBE cost? We did 3 of them this year. That's how I know how much it cost. This academic year. This fiscal year, which roughly aligns with the academic year. WPI's fiscal year goes July to end of June. So yeah, all right. But anyway, so we've got our origin. Once we've got our origin, what do all toolpaths have to have? Yeah.
I wanted to make an argument for moving the 0 on this particular part.
Oh, there's plenty of places where the 0 could be on this part. What's your argument?
So when
I would almost never pick that spot.
Yeah, when I make parts, I usually like to make it in the X and Y center. Still on the top of the stock usually, but by putting it in the part X and Y center, that allows for like a larger variation in stock size.
It gives you a little bit more opportunity to screw up both in setting the offset, so in locating the XY0, and in having your stock be a little bit not quite the right dimension. So we can move that to here. I often put it in the center also. One of the nice things about using CAM software is you can write your entire program without really considering where the 0 is. And at the moment when you decide to go set up the machine, you can think, what's the best place to put the 0? And you can move the 0 to the place where you want to put it to make your setup task more easy, as long as you, after you move this and make any changes to the program, then you send the code to the machine, right? So if you've already sent the code to the machine, you can't just move stuff randomly in the CAM software. The machine won't know. But if you make changes in the CAM, which is one of the reasons we put computers at all the machine tools. So you don't have to go anywhere to fix your CAM program. You just pivot your feet and do that. So yeah, I often put it in the center. It gives you a little bit more leeway in figuring that out. Whether you put it on the top of the workpiece or on the top of the part, you just have to make sure the person doing the setup knows which one it is, right? This is interesting. So with the way I drew this, I was envisioning a tool path that would sort of go around here to make the 4 sides, right? 1, 2, 3, 4 sides. A facing path on the top to make that 5th side, and then make a little pocket here to cut out that cutout. That was the tool path I envisioned. So we'd go around it down to this level or so while clamping on it here, right? So the part we're cutting would be up above the vise. Then I imagined the next operation. See my stock material. So here's my workpiece, or my part rather. And my stock material now will be like that. And I clamp it in the vise like this, and then have a facing pass that removes that material. That was sort of what I was envisioning with this setup. When we do this second setup, where should the 0 be? Because each setup's got to have its own work 0, right? So when we flip that part over, where should 0 be? This has a very definite correct and less correct answer. Where do I want to put 0 now? I flip the part over. Yep.
The bottom of the part.
You want to put it on the bottom of the part. We could still put it in the center if you want. Right? We could project. Is that what you mean?
Sure.
Or it could be one of the corners.
Yeah.
But just to stick with our theme of putting it in the center. Is he right? Yeah.
I think yes, because ultimately we're only really caring about the height, because all of the other cuts should already be done.
Right. So we want to put it here, and if we don't put it here, it's going to be difficult for us to make a good part. If that dimension matters, right? That was 1 inch. So if this is plus or minus about a thou or tighter, you've got to put it down here. If you put it anywhere else, if you put it here, it's easy to set up, right? Pain in the ass to set up, actually, because is at the center of this. And what did those edges look like when you did the other operation? Were they bandsaw cut edges? So I agree. I want to put it on the bottom. Maybe I'll put it on a corner so I can put a part stop and I can come up over against the part stop. But I definitely want to put it on the bottom so that when I program this tool path, I get a part that is the height that I wanted. Does that make sense to everybody? All right, so we've got to pick our origin. On the initial setup, really we just pick the origin for convenience for programming, for convenience for setup. Where we put the origin really matters on the second side after you flip it over, because you're going to lose your alignment. You got to know where it is. And 2, it controls your ability to make the part the right height. All right, so we've got our origin set for our operations. What else does every operation have?
In the chat, you have where you enter the material.
So you've got to enter the material. So where you come into the material, and so we'll call that maybe lead in. So we're going to have that. That's not the next thing after the 0, though, that we have to have.
The speeds and feeds for your tools.
So we've got to have speed, feed, depth of cut. So I think the enter and exit was what they meant on the chat group, and I agree. We have to have that. We've got to have that. We've got to have speed, feed, and depth of cut, and this will define our geometry of our tool path. Before we enter the material, what do we have to have? Yep.
You have to identify the tools.
We have to have a tool. So we have to call a tool. We have to say what tool we're going to use. Between putting the tool in the spindle and entering the part, we actually have to approach. So we tool change. We move from the tool change location to the place where we want to enter the material from. It would typically do this as a rapid move. Right, so we'll have the tool move as fast as it can from the tool change location to just next to the part. And the reason we go as fast as we can is because we can. Right, moving fast, right? That's why I don't know why like the gas pedal in the car has so much motion to go through. It should just either be on or off, right? Either as fast as I can or not moving. You guys laugh. My grandmother used to drive that way. Like, I don't know if you've ever ridden in a cab in Manhattan, but my grandmother drove like a Manhattan cab driver. I think it's because she learned to drive in Manhattan, but the throttle was down or off. All right. Tool, it's got to approach. We're going to go as fast as we can, then enter the material. And so when we're entering the material, we want to think about how the tool's engaging with the workpiece material. So we get that tool spinning at, I don't know, how fast you want to spin the tool. I guess before we even do this, we'll just spin the tool. We need the speed before we even get over there to touch the part. If the tool is spinning when it touches the workpiece, the tool has a chance to survive. If the tool is not spinning when it touches the workpiece, it breaks every time. So if you're moving the tool around near the workpiece and you want to take that into account. All right, so tool speed, approach, enter the material, feed speed, depth of cut, which makes our tool path. After we do the tool path, we're going to exit and then go home. So every tool path, and so we may not go home at the end of the tool path, right? We may go to the start of the next tool path if it uses the same tool. If it's going to use a different tool, then from here we're going to go to the tool change. While it's in the tool path, so when it goes to this approach to the place where it enters from, this is the clearance. Typically it's a clearance plane. So it'll come down to a plane above the part, right? So when you're programming and you're running your program and the machine crashes, has anybody experienced that actually in the lab? Anybody crashed the machine, broken something you have?
Not broken something.
Yeah, it's a crash if you cut something you didn't intend to cut. So you successfully cut something, but it wasn't what you meant to cut. What was it?
We were like doing a facing off, and we had forgotten to offset our Z, and it like plunged right into our part, like pretty deep. And we're like, oops, gotta
So could you save the part?
No.
Then you broke something. You broke the workpiece.
Yeah.
Didn't break anything too expensive. Nobody else has crashed the machine? You must have crashed the machine. Yeah, see? You get to raise your hand. Anybody online crash the machine? Nobody's fessing up to it. My best crash. I'll share this. I think it was also my most expensive crash. I haven't really kept tabs, but just imagining, yeah, it's definitely my most expensive crash too. It's my best crash. It was a Saturday morning. It was June. It was 2016. I could figure out exactly which day in June because there's only a couple of Saturdays in June, right? Four Saturdays. It was really nice weather. It was like a nice, warm, sunny day. The overhead door was open to expose the shop to the outside. I had been in front of the machine for about 4.5 hours setting it up. And I said to my business partner at the time, I said, I'm ready to go. I'm going to run these parts now. And he said, don't you want to do a dry run first? And I said, no, it'll be okay. Here. Let's see. Cycle start. Feed hold, right? Cycle start, feed hold. Emergency stop. And so I said, hey, I'm ready to go. Pretty excited because I just spent 4 hours setting up the machine. I'd made some test parts. I knew that it was going to make a good part. And we had to make 80 of these by Monday. And so I said, I'm ready to go. He says, don't you want to do a dry run? I said, nah, it'll be okay. Cycle start, spin around. I got about this far around and it didn't make the right noise. Right? It made a valid noise. Not the noise I was expecting, because I was expecting to hear the tool changer. And what I heard was the spindle spin up to about 5,000 RPM. That wasn't the noise it was supposed to make. So cycle start, turn around, hear the noise, e-stop. Yeah. So the $2,000 grinding wheel that was on the spindle, destroyed. The fixture that I just spent 4 hours setting up and getting perfect, gone out the door of the machine. The door was open so we could see, so we get access. It's from out the side door. Gone off the table, completely gone. Fixture on the ground outside. I did find the workpiece. Workpiece was fine. We salvaged that workpiece. We still had to make 80 parts by Monday, and now we had to start from scratch, rebuild the fixture, put everything in the machine. Yeah. That much time. Heard the wrong noise. I knew it was the wrong noise. And you know what I didn't do before I pressed cycle start? There's a sticker on all the Haas machines in Washburn. I didn't even get a chance to check distance to go. It was way faster than that. Press reset before you press cycle start. I had stopped my previous dry run setup thing partway through the program, and when you press cycle start, it will restart wherever it was in the program, which required the spindle to be down next to the, yeah. Anyways, so we made it. By the way, we made all 80 parts. They were delivered on time. I did have to drive to the customer site on the Monday morning with the parts in the back of the car, but we did it. Didn't sleep the whole weekend. It's not quite true. We took turns sleeping in the car in the parking lot while the other person kept the machines running. All right, so that's all toolpaths have all those things. So this can't be that hard then, right? So what are we going to do for Thursday? What time is it? It's about time. What are we going to do for Thursday? Yep. I said some things, right? Good. He remembers. Go ahead.
Pick the stock material, size, material.
Yep.
Budget or price for it.
Get some budget prices. Don't order it. We might have it on hand. But do find out how much it will cost if we do need to order it. Say again?
Model.
Now, in order to get stock material, what do we have to do first? We have to decide what processes we're going to do, right? So we need solid models. We need to know what stock material you're going to use. We need to know what processes we're going to use on the stock material to make our parts. Now, you guys got 32 parts. Whoever's over here doing the chess thing. You the chess group? Yeah. You get 32 parts, right? Most of the processes are going to be similar, though. So identify which parts are going to be just turned, which parts are going to be turned and milled. Okay. If you're going to make different size parts, different pieces of material, different processes for those different materials, identify those different things. Likewise for the can crusher group, you're probably not going to have one common piece of stock material that you make lots of pieces out of. You're probably going to have different things. So plan the process. So I want to, instead of decide process, let's call it a process plan. Now, we kind of glossed over that process plan a little bit, but when we did our all tool paths, we came down with feed speed, depth of cut, right? And before we know feed speed, depth of cut, we got to know tooling. So in order to really make a process plan, we've got to pick our tooling, and we've got to know what the feed speed and depth of cut should be to use that tooling in our stock material. Right? So part of our process plan is going to include tooling and a description of the tool path. So I don't need to have the tool paths, right? You don't have to have gone in the CAM software, used the CAM software to generate. You can go ahead and do that, but it's not required for Thursday. But tooling and parameters. So that when you go to do when you actually get to do the CAM, you don't have to figure this stuff out, right? You say, all right, we're using a half-inch end mill. The half-inch end mill spins at 6,000 RPM, and it's going to have this feed speed, depth of cut, right? So know what that stuff is for the tools you plan to use. How do you pick the tooling? We haven't talked about that in class yet, but you guys have seen it before, most of you. So if we're focused on milling now, you guys that are doing turning stuff, can they talk to you about turning, feed speed, depth of cut, stuff like that, or should they go to James?
I can do basic turning.
Okay, talk to Hayden and or James to figure out exactly what you need to do. But let's focus on the milling parts right now, and this will help you for your milling stuff too, right? So if we're defining a milling tool, if we're choosing a milling tool, what are the factors that we need to consider? Yep. So how the total depth that we need to cut to? I think we call that AP max in the tooling catalogs. It's how far down into the material can you cut with that tool. Now, if we need to cut down here, so let's say this is 5 inches. And we need to do a side milling operation all the way down this 5 inches. We could get a tool that's got flutes that go down 5 inches, right? We could do that. Somebody makes that tool. We could buy that tool. Or we could get a tool with a reduced shank, where we've got maybe a cutting depth of a 1/2 inch, but it could go all the way down 5 inches, right? So those are different ways that you can get that AP max. So how deep can you possibly go? So you'll want to consider that. How far down would we like to go? In the ideal world, how far down would we like our tool to go in the workpiece? 0, right? The least depth we have, the better, because this tool is going to deflect, right? And so you've got a cutting force applied here. What's the deflection equation? The little delta equals, anybody remember? It's deflection of a simply supported beam. So it's gonna depend on the force, cutting force, right? Yep. So there's modulus, and there's the area moment of inertia underneath, right? Is that I? And then that I is going to depend on the geometry of the thing, right? So it'll be radius and stuff like that. Length is cubed. So don't forget length is cubed. So the longer it is, the more impact that'll have on deflection. Now the deflection will make it the wrong shape, right? The other thing it'll do, though, is it'll deflect, and then the force will be a little bit less, and it'll deflect less, and then it'll be more, and it'll deflect more, and it'll be less, and it'll deflect less. And you can set up a resonance, and it vibrates. Who's ever walked through the lab and heard it screaming? Heard one of the machines really screaming? Yeah, that's because somebody set up a resonance in the tool. And so it's chattering on the workpiece like that. So the least depth possible. Now, because the design dictates how far down we have to cut, right? You could hold it different orientations, but the design is going to define that. What do we do to compensate for the fact that length is cubed? So this has got a radius in it. I forget the equation for I for round, but I know it's got R. Is it R to the 4th power somewhere in it? Anyway, this radius of the tool is in that I. So if we make a ginormous radius, it must be underneath because it makes I smaller. If we have a bigger diameter tool, it will deflect less, right? So we've got to have our AP max, our diameter. So what diameter tool do you want to use? What diameter tool do you want to use? This is a general rule. Yeah.
The one that you don't have to put in a new fixture.
The one that's already set up, you mean?
Yeah.
All right. So that's fair. But you want to use the biggest diameter possible, or the biggest diameter reasonable. So if you had a 1/2 inch tool and an 1/8 inch tool that both had the same AP max, which one should you use? Well, you want to use the biggest one possible, and so if you've got an internal corner that you've got to cut, the diameter of the tool can't be more than twice this radius, right? Or right, if the diameter of the tool is bigger than that, it can't fit in that corner. But you could rough out a bunch of material and then come back in with a smaller tool and just clean up the corners too, right? So you're going to pick your processes. You're going to pick your tools by diameter, the tool material. We're going to use solid carbide tooling because we have a bunch of that. You could argue that your particular thing maybe needs a special tool, but I doubt it. Material, diameter, and then just the geometry of the tool. So the number of flutes in the tool, the spiral, the helix on those flutes. And that's going to depend on the material that you're cutting, things like that. Do you guys know how to go to the mfelabs.org and look for tooling? Somebody from each group? Is there a group that doesn't know that? If you don't, talk to Hayden or James, or just go to mfelabs.org and search for it. And that'll tell you the tooling that we tend to have on hand. If you need to use an especially small tool to make detailed features, you're going to want to make sure that we actually have that because the small ones break faster. What else? All right, so process plan, tooling, parameters for those tools for making your thing. That's what I want to see for Thursday. So we'll do a presentation. Last week, in the assignment, did I tell you to make a Google Slides presentation and then submit the link to the Google Slides? Was that part of the instructions for the submission? If you do it as a instead of just linking, like sharing your slide presentation, if you go to File, Publish to the Web, and you create a link to the published version of your presentation, and then submit the link to the published version of the presentation, then we won't have to have everybody log into their own Google account. We'll just click on the links. Does that work for everybody? And then you can, I guess, unpublish it later if you're worried that the world is going to see what you put in your presentation. I don't know. I have thousands of published Google Slides presentations, and I don't think anybody ever looks at them, except for maybe you guys. I have found some of them on Russian websites. And I don't know, because I think, well, I guess it was free there too, but you could have gotten it for free on my website too, so I don't know. Does that look good for Thursday? We also want to know, is there something that you're hung up on and stuck? So for Thursday, present this and tell us as a group what you need help with, so that maybe somebody in the class knows how to answer your question. Maybe I know how to answer your question, or we can figure out how to find out the answer to your question. I think I'm good. You guys good? Thank you for being here. Let's try to start right on time on Thursday, so we give everybody 10 minutes to present. Good 10 minutes. And what order should we do the presentations on Thursday? Group 1 through 5? That's the easiest order to do. Okay, you guys are stuck in your presentation order for Thursday.